Okay, hello everyone. I feel it's a great honor for me to give a talk here. My name is Zhiwen Li. Sorry. I'm from Beijing Normal University, uh, and I'm a second year master student. Today, I will present our work on a new approach to identifying RSGs, red supergiant stars, and asymptotic giant branch stars in metal galaxy, a case study to NGC 6822. My collaborators are Professor Biwei Jiang, Research Ming Yang, and Dr. Yi Ren. So, RSGs are massive, helium-burning massive stars, as shown in the left figure. After leaving the main sequence, they evolve horizontally to the right on the CMD and concentrate as a slip branch. The middle figure shows the decontaminated CMD of the small Magellanic CLouds. In the figure here, we see a clear branch of the RSG as shown by the red dots. So we can easily select the RSGs on the CMD by these cut lines. However, because we located on the disk of the Milky Way, actually there are a lot of foreground foreground dwarfs inside of the target galaxy, as shown by the right panel. The gray dots represent the foreground dwarfs of the Milky Way. Hence, the key to identifying RSGs is to remove the foreground dwarfs of the Milky Way. Once we obtain a decontaminated CMD, then we can identify the RSGs on the CMD using such cut lines. So there are mainly two methods to remove the foreground dwarfs. One is the color diagram method. We call it the CCD method. Such as the B minus V, V minus R diagram, and the R minus Z, Z minus H, and the J minus H, H minus K diagram. In both these each CCD, we can see there is a obvious bifurcation between the RSGs and the foreground dwarfs. The lower branch is a dwarf branch, and the upper branch is RSG and the AGB branch on the CCD. So we can remove the foreground dwarfs by removing the entire dwarf branch using such boundaries. And the other method is the Gaia astrometric method. We can select the member stars of the target galaxy by, on the proportion diagram because they are concentrated on the on this diagram. Along with the parallax constraints, we can remove the foreground dwarfs where. However, both these two methods have their own limitations. In this figure, the red dots are the RSGs of the SMC identified by Ren et al. 2021b. Here we see they have mixed into the dwarf branch. This is because the color of the RSGs will become bluer and they will mix into the dwarf branch. Hence, for CCD method is poor at distinguish RSGs in metal galaxies. And the Gaia astrometric method is powerless for the galaxies beyond the SMC. Hence, in this work, we aim to find a new combination of the CCD method and the Gaia astrometric method to identify RSGs in distant and metal galaxies. We use the Galaxy NGC 6822 as a case study because it's low metallicity and its moderate distance make it a good laboratory for our study. Its iron to hydrogen ratio is about -1 and its distance is about 500 kpc. Our research region is inside the red rectangle. We use astrometric data from Gaia DR3 and the near-infrared data of the JHK band from the open time observation of the Euclid telescope. It's a 3.8 meters telescope, and the optical data of the RZ band from the Pan-STAR DR2. So in our method, for the sources with RZ H band, we define the borderline of the dwarf branch. we select a reference region as shown in this figure, as shown by the blue rectangle. Then we obtain the spine points of the dwarf branch by Gaussian fitting in each R-C bin. Then by removing these points appropriately, we obtain the borderline of the dwarf branch as shown by the red dashed line in this figure. And second, we trace the empirical region of the RSGs as shown in this figure. Based on contouring the RSGs of the SMC as shown by the red dots, we obtain an empirical region of RSGs on the R-D, D-H diagram, as shown by the purple curve in this figure. It denotes the potential region of the RSGs on the CCD. Besides, the position of this region should change with different metallicity, because as we mentioned before, the color of RSGs will become bluer as the metallicity decreases. Hence, as shown in the lower left figure, we fit the variation of the mean color of RSGs in SMC, LMC, M33, and M31 with the metallicity. It tells us how the empirical region of RSGs shifts on the CCD. Besides, we consider rotation factor of the empirical region because the slope of the RSGs will become bigger as the metallicity decreases. And as shown in the right figure, here we see the traced empirical region is fits well to the observed RSGs in different galaxies, such as SMC to M31, in different galaxies with different metallicity. And third, we remove the foreground dots on our CCD. This figure shows the red dots are the capped sources. And in our work, any sources within the empirical region of the RSGs are kept, even if they have mixed into the dwarf branch to make our sample complete. And for other sources, once below the borderline of the dwarf branch, they are removed in our sample. And for the sources only with the JHK band data, we clean them on the J-H, H-K diagram. The procedure is same as in the R-D, D-H diagram. First, defining the borderline for the dwarf branch. Second, tracing the empirical region of RSGs in this CCD. And the third is removing the foreground dwarfs, the red dots, also the capped sources. Then we obtain these sources, then we further clean them using Gaia astrometric data. This figure shows we make a 2D Gaussian fitting for the proportion distribution of these sources, and we obtain elliptical constraints as shown by the ellipse in this figure. And any sources falling within the ellipse are kept as shown by the red dots, and the sources falling within the ellipse after taking account of errors are also kept to make the sample complete, as shown by the blue dots. And this formula shows our parallax constraints. That means we remove the closed sources with precise detection. And here we have obtained a decontaminated and complete sample of the member stars as shown in the upper left figure. In this and we can identify RSGs and AGBs in the CMD using such boundaries. And the orange dot in this figure shows the identified RSGs. The blue dots are oxygen AGBs, and the green dots are the carbon AGBs, and the purple dots are the extreme AGB. And the middle figure and the right figure represent the they are the complementary sample that present the sources only satisfy the CCD criteria or only satisfy the Gaia criteria. And in our complete sample, we have 1,184 RSGs candidates with in the lower row figures, they present the corresponding potential contamination in each CCD. They are obtained by performing a same procedure in the reference region as shown by the blue rectangle, and it provide us a contamination rate of our RSGs of about 20.5%. We also provide a pure sample of our of the RSG. As shown in the lower left figure, the complete sample means we keep the sources that have mixed into the dwarf branch based on the empirical region. However, in our pure sample, we remove any sources once they are below the borderline of the dwarf branch. And in our pure sample, the upper row figures present the results of the pure sample. The same as in the last slide, and the lower row figures present their corresponding contamination on each CCD, on each CMD. And in our pure sample, there are 843 RSGs in the sample with a contamination rates of about 6.5, and there are also different AGBs are provided in our sample. Okay, we make a comparison with previous works. Yang et al. 2021 identified 234 RSGs in NGC 6822, mainly by R-D, D-H diagram. And there are 213 sources are matched with Yang's work. For the 21 mismatched sources, 14 sources are classified as other stated populations on the CMD in our work. Because the slight difference of the cut lines, and 7 sources are removed as foreground sources in our work. And Zhiwen et al. 2021b identified 465 RSGs, mainly by G-H, H-K diagram. And there are 297 sources are matched with Zhiwen's work. For the 168 mismatched sources, 87 sources are classified as other stellar populations on the CMD, and 81 sources are removed as foreground sources in our work. And we give an estimate of the newly identified RSGs in our work, about 600 and 450 RSGs are newly identified in our work in the complete sample and the pure sample respectively. Okay, I'll show the summary here. We construct a complete sample of RSGs and AGBs candidates in the MetaPro Galaxy NGC 6822 by combining the CCD method and the Gaia Astro method to remove the foreground contaminants. 1,184 and 843 RSG candidates are identified in our complete sample and the pure sample with contamination rates of about 20.5% and 6.5% respectively. We will apply this method to more local group galaxies to extend the RSG sample in a wide range of metallicity. It's important for us in the future. Okay, thank you for your attention. Thank you very much.
Nice work, first of all. So 2 questions. You mentioned something about completeness. What can we say about how complete we are about these RSGs in these catalogs? And yeah, also because I'm using such catalogs for supergiants defined by color. The contamination you're referring to is about foreground contamination, right?
Yes,
because
the first question, the complete, because in the MetaPro Galaxies, RSGs were mixing to the dwarf branch. And if we use the traditional CCD criteria, this borderline of the dwarf branch will remove all of the potential RSGs that have mixed into the dwarf branch. So in our work, based on this empirical region of RSGs, we keep the potential RSGs that have mixed into the dwarf branch.
Yeah. Okay, cool. And the other is about the contamination from AGB stars in these color magnitude diagrams.
Okay.
Yeah, because AGB stars can be variable, also can be bright, and can occupy the regions around all this CMD. So can we quantify this somehow?
Oh, okay. We don't provide the contamination from the AGBs, but we now have a method that in the because we identify the RSGs in the infrared CMD, and there is a good method to distinguish AGBs and RSGs that is in the optical infrared. Actually, the optical CMD can distinguish the RSGs and the AGBs well, because the AGB have more thick the dust and make it redder on the optical CMD.
Okay, thanks.
Thank you for your question.
I see Philip Massey has a raised hand on Zoom, so if you'd like to go ahead and unmute.
Hi, thanks for that very nice talk. As you know, our group has been identifying red supergiants in NGC 6822 for a couple of years, and in our paper that our very good undergraduate, Shisha Lina Dimitrova had in AJ in 2022,
yes.
We found that we were not as brave as you were in terms of how far down. As you know, we used exactly the same data set. We used UKirk data, and we did a covariant analysis using Gaia to remove foreground stars. But we found that the AGB contamination, once we got down to like 16th magnitude or so in K, really became overwhelming. That there is, after all, a range in color of the AGB stars, and because after all, they represent a range in ages as you go down in magnitude. So I wondered how certain you were that you were actually removing AGBs down to the level, all the way down to the tip of the red giant branch. If that's correct, that's really remarkable. Thank you.
Oh, okay, thank you for your question. Yes, in the UKirk data, because the quality of the photometric quality, there are actually some AGBs mixed into the RSGs, and you mentioned the work of Dimitrova, and we compare with the work, and a good agreement about 46 sources are matched, and the main question is that the AGBs will pollute the RSG branch. Actually, we found this question, and we plan to clean the RSGs using optical diagram in our future work, and this is our plan to clean this RSG.
Thank you very much, and good luck in your future work.
Okay, thank you very much.
Other questions?
Hey, nice work. I'm interested in the brightest red supergiants that you see and how that varies with metallicity. Do you see any evidence for the most luminous, for a metallicity dependence of the most luminous red supergiants?
Okay, sorry, the bright stars and what?
Do you see any evidence that the brightest red supergiants, their luminosity varies with metallicity compared to the other environments that you showed on the previous slide?
Their metallicity.
Yeah, so this is a low metallicity galaxy, right?
Maybe their metallicity is higher than the -1, and I don't know the actually metallicity of the bright stars. And we can talk after the presentation.
Okay, yeah, that's still clear. Thanks.
Okay.